Good evening to the Lobo Living Room, and this event sold out tonight, and I was trying to figure out why, and then I realized there was going to be free beer, and so anyway. So the Lobo Living Room, I'm sure that there are a number of you are long-standing attendees of it and so forth, but a number of you may not be. The Lobo Living Room is a program sponsored by the UNM Alumni Association that started about 5 years ago. And the very first Lobo Living Room that they did was a behind-the-scenes look at the production of The Lion King when they were doing it here in Popejoy. Since then, that was a colossal success, and they took people behind the scenes and showed them how a roadshow play like that gets put on. But since then, it's featured lectures, tours, performances, and behind-the-scenes tours both on and off campus, all of which have some tie to UNM. I got introduced to the Lobo Living Room relatively recently, and I've now been to several, and it's always been just a colossally wonderful experience because every single one of them highlights something that's really cool and really notable and really fun about UNM. And the purpose of the Lobo Living Room is to do just that. It's to engage the UNM alumni, students, faculty, staff, and the community by highlighting the talents of our wonderful alumni and also some of the really neat things that are going on at the university. My name is John Brown, and I'm the president of the UNM Alumni Association, which is how I got roped into doing these introductions, which I'm really happy to do because I'll be partaking myself in a few minutes. And so I'm really pleased to be here to welcome you to tonight's really fun Lobo Living Room. And tonight, what's really kind of neat about it is it's part of our Wolfstock Peace, Love, and Lobos Homecoming Week festivities, which we're in the full swing on, and lots of fun things have been going on, and many more will continue to go on through the weekend. But you're in for a real treat tonight as we settle in to learn about the scientific processes which make up, for many of us, our favorite beverage, beer. And being a university, of course, we have to have our resident scientists here to tell us about it. Now, we all know beer's been around for a really long time. You'll learn about, and tonight you'll learn about the 4 major elements and the chemistry of making beer and all that sort of thing. And it's going to be an awesome program. But before we get started, we have a little swag, and we have a traditional drawing at all Lobo Living Rooms for door prizes. So pull out your tickets, which I think you all got when you registered. And we'd like to recognize UNM Sub Catering, who is donating 2 $25 gift certificates by the Lobo Card Office. These are good for any dining services on the campus, including the brand new tap room, which I'm sure you all walked by when you were coming in, draft and table. So now is a good time to note that the following Lobo Living Room draft and table will be open for extended hours to introduce their new facility. Also included in our drawing are t-shirts from the UNM Department of Chemistry and Chemical Biology, who is our academic sponsor for the evening. We also have a drawing for UNM alumni swag for those of you who left a business card. So here we go.
Our first 2 drawings will be from your tickets, so you already have a ticket ready. John?
Okay, I got 3 here. Put that one back. 330124. All righty. We have a winner. Okay, 330949. We have another winner. All righty.
Up a little bit here. Business card.
Okay. Winning coffee. Just winning coffee. Who's here from, there we go. All righty. Okay, now it's my pleasure to introduce to you the department chair of the UNM Department of Chemistry and Chemical Biology, Dr. Jeff Rack. Dr. Rack received his BS in chemistry at Clemson and his PhD in chemistry at Colorado State University. He was a postdoctoral scholar at Caltech in 1999 and a postdoctoral fellow in 2001 at Los Alamos National Labs. Dr. Rack has been at UNM since 2015, and he will then introduce our featured speaker, Dr. Martin Stone.
Thank you. So I assure you that there was no collusion. The spouse of the departmental administrator for chemistry and chemical biology was the first recipient of the awards tonight, but I don't think it was rigged in any way. The Department of Chemistry and Chemical Biology is very proud to co-sponsor this event and to introduce this evening's lecturer and to show you how to drink beer properly, or at least in a more enlightened way. Chemistry is the science of transformation. Chemists transforms atoms into molecules to make drugs and fuels and other useful products like plastics. All of you are chemical machines. You eat fruits and vegetables and meats, and you turn that into energy so that you can think and breathe and move around. So indeed, you do eat chemicals for breakfast, and you should do so proudly. You practice chemistry, all of you practice chemistry in your daily lives when you are in the kitchen cooking, and in fact, brewing is just a natural extension of that. And us chemists are happy to let all of you practice chemistry. We'll let anybody do it, including engineers. And so it is my great pleasure to introduce to you Professor Mark Stone, Dr. Mark Stone, who's an associate professor in the Department of Civil, Construction, and Environmental Engineering. They recently had a name change, so he's very proud about his name change, I understand. So he's a registered professional engineer and a diplomat of water. His career goal is to improve the balance between human society and natural environment through research, teaching, and service. His research interests are focused on the interfaces between engineering, ecology, and geomorphology. Dr. Stone has been involved with dozens of field laboratory and computational research projects covering topics such as environmental flows, ecosystems, wave attenuation, fish passage, design guidance for steam restoration, climate change impacts, the list goes on. More important is he has a long marriage to beer. He started brewing beer approximately 15 years ago when he was a graduate student. One might say he came by it honestly, as all of his lab mates were also brewing beer. Presumably not in the lab, but you never know. That's where chemists normally do that, is in the lab. His fondest memory of brewing is when he brewed beer with a friend of his on his 50th birthday. And so I don't know any more about that, but hopefully he'll tell us more about that. Professor Stone, please.
All right, thank you everyone. I'll find the right distance for this, but thank you everyone for coming out this evening, and I'll try to figure out how to use both hands, one for the mic and one for this, and I also talk with my hands, so this is going to be quite a feat for me. But I do appreciate everyone coming out this evening. It certainly is true that free beer really brings the crowds, and I appreciate that. I also want to thank, first of all, the chemistry department for basically having this idea to hold this event, the Alumni Association for pulling everything together. We have 4 breweries here in town that donated the beer for this evening's event, so we certainly appreciate that contribution as well. So with that, I'm going to jump in. The plan tonight is that I'm going to go through 4 little mini lectures that each one of those will be followed with a little taste of beer related to the material. And then I'll close out with one last small lecture that will highlight some ongoing research that I'm engaged with in the beer world. Okay, sound reasonable? Good. That's all I have. That's the only plan I have. Okay. All right. So here's the mystery that we're going to try to unfold to the degree that we can here in our time together, and that is, how can we have these 4 really simple ingredients? Malted barley, water, hops, and yeast is such a simple combination, and produce such an amazing multitude of beer styles. Well over 100 recognized beer styles, and within each of those, of course, incredible variety. So what is it that allows, as Jeff called it, transformation of these raw ingredients into something that is so magical and that touches so many of our lives? So what I'm going to attempt to tie together is those ingredients with the process itself, because that is the transformation. It's how we manipulate the conditions in order to pull out the different characteristics that generate that diversity for us. This is a highly simplified representation of the brew process, but I'm highlighting the key steps, and I'm just going to jump right into it. So we go from malting, mashing, boiling, fermenting, and then finally we get to enjoy. And I know everyone wants beer already, so I'm going to get right into it. Okay. So the first step actually happens long before it ever reaches the brewery, and that is to take barley, which is the main ingredient used in beer, or the main grain used in beer, and to turn it into something that the brewer can actually take and make a nice product from. And this is so fascinating to me because seeds are nature's ability to store energy in such a magnificent way. Right? It's the little power cell there, all this energy stored, but it also preserves it in that form in a way that is hard to get anything out of it, because you don't want your plants just growing when it's still in storage. So the malting process is really about fooling Mother Nature into releasing all the goodness that's stored in its seeds. That's really what the process is all about. So what the maltsters do is they add some water, they let it drain, they add some water, they let it drain until the plant actually starts to grow. And we have this thing called an acrospire that's actually just the little seedlet, the little rootlet that starts to go. And it starts this transformation within the endosperm itself, where the carbohydrate chains, which are just long sugars, and the proteins move from a state where it's extremely stable, it's locked up in tough cell walls, and actually starts to become available. But you don't want that to go too far, because we're not trying to grow a crop here, right? We want to turn it into wonderful beer. So the next thing the maltsters need to do is dry it, and then they take it through different processes depending on what they're trying to accomplish. So they can kiln it just to dry it. They can stew it and heat it, which results in caramelization, or they can roast it. And this is just a few of the examples of the tremendous range of malt products that these maltsters can produce for us. There are 2 important, very complex chemical processes going on behind this. Maillard reactions, which all of you are familiar with. It's what makes the crust of your bread so delicious. And the other is caramelization, which makes this sticky bun look so delicious as well. Stay focused on beer. Don't let the sweets distract you. Okay. But there are complex biochemical processes that are going on to drive these things and produce these wonderful products. So at the end of the first round here is to keep in mind that what comes out of the malting process is we're putting raw barley into it, and what we're getting out of it is these starches, which are really just long chains of sugars, enzymes, which I'm going to spend more time on in just a little bit, nutrients that are also critical for healthy yeast, and other flavor and color compounds that contribute to the beer. Okay? And with that, I want to make this first one quick, because I know everyone's going to want beer, and hopefully the beer is ready to be distributed. But one of the best styles to get an appreciation really for what malt does for us is the classic Czech Pilsner. Truly the king of beers, not the one that you see necessarily on the football advertisements on on a Sunday afternoon. But the Czech Pils has inspired beers across the world. Over 90% of the beers in the world that are served today were derived from the Czech Pilsner. And what makes it special is that it has just a very, very simple, what we call a malt bill. Okay? So it's the lightest of the roasts, and it really emphasizes the malt character. So it's like coffee. If you roast coffee for a long time, what you taste is the roasting process. If you roast coffee for just a little bit of time, you actually taste the bean, and you get a better sense for where it came from. And that's completely true with this as well. So I don't know exactly what our protocol is here, but for whoever has beer, let's run the gauntlets and let's push some beer out. The Pilsner that we're going to enjoy this evening, it comes compliments of Canteen, located over in the Brewery District off Aztec. This particular beer won silver at the World Beer Cup in 2016, which really drives home that it's an exceptional version of this beer. And when you do get a chance to enjoy it as the beer makes its way around, again, just really try to focus on the malt character, okay? All right, and for the sake of time, I'm just gonna keep on moving, so hopefully beer makes it to you shortly, okay? All right, so after we're done with the malting process, this is where water enters the brewing world. And we go into the part of the process that we call the mash. And the mash is really just, we crush the grains so that it can saturate and hydrate. And we add hot water. And the goal of this entire process is to make sugars. Okay, we want to take, the seeds are loaded with starches, and we want to make sugars. And why do we want sugars? Because the yeast, we're going to feed the yeast, right? The ultimate goal here is we're making yeast food, because the yeast are going to do the work for us. Okay, so we've got these long starches that are really just we have two primary starches that are found in barley, amylose and amylopectin, and these are just long chains of glucose. Okay, so just long chains of sugars, and our goal is to break these things down into something that's a little bit simpler. So we need to cut them up. And unfortunately, we don't have scissors quite that small. This is not up to scale. This is a blown up version. It's just a representation. So what we rely on is what nature provides us, and that's amylase enzymes. Okay, and nature was really generous with us on this one because the amylase enzymes are also in the malted barley. Okay, so how nice of Mother Nature to package these things. Okay. So that acts as a scissors, and our goal is to generate these shorter, simpler sugars out of the process. Okay? I'm going to go a little farther into these reactions. For those of you who remember some of your basic biology, you'll remember that enzymes are sensitive to different environmental factors because they'll fold and unfold in different ways, and they'll only be effective when they're in the right range of conditions. And for our amylase enzymes, our primary concerns are that we're in the right pH range and the right temperature range. Okay? And we actually have a couple of subcategories of these that we're working with. One we refer to as beta amylase. And the way beta amylase works is it just chops off the last two glucose molecules repeatedly and works its way down the chain. And I put together, I want to hear an ooh, because watch this. Ah, okay. Hours. It took me hours to get that. Okay. Totally cross-eyed. Okay. But that's what it's doing. It's just chopping off those last two repeatedly, and working its way down the chains. So back over to our temp and pH, it sits right around there. So it's most effective between about 135 degrees Fahrenheit and 150 degrees Fahrenheit. And the consequence of really optimizing this particular enzyme is that because we're creating really simple, oh, by the way, these are the maltose, right? The doubles are the maltose 2-glucose. Those are really digestible by the yeast. And as a result of that, the yeast can eat up pretty much all of the sugars. There's very little sugar left behind, and that's why we get a dry beer. So if we ferment, or if we mash on the cool side, we get a dry beer, okay? You might see where this is going. Its partner is the alpha amylase, okay? It works a little bit differently. Get ready. Ah, yeah, okay. It's just Edward Scissorhands, okay? It just chops away, right? It doesn't neatly come in and clean off the last two like the beta amylase. So it makes sugars of all different lengths, okay? So we can get glucose, maltose, maltodextrose, and even longer glucose chains. Some of which are easily digested by the yeast, some of which the yeast really has trouble digesting. So it sits up in this range, in the warmer range, and the consequence of being up in that warmer range is that we get a sweeter beer with more body to it, okay? So the brewer's range is somewhere in there. Most mashes are executed between about 145 and 155 degrees, and a pH between about 5.3 and 5.4. So that's what we need to generate when we're running our mash. The temperature part in terms of process is pretty simple. If you need it warmer, you heat it a little bit. If you need it cooler, you cool it a little bit. pH is a little bit more tricky, okay? So let's dig into that just a touch more. I was wondering what everyone would look like when they saw these pictures, okay? On this side I have, does anyone recognize what I've got there? It's a spring. It's a travertine hot spring, okay, which is loaded in carbonates, okay? High alkaline systems. On this side on the left side I've got some roasted malt, okay? And I want to talk about how these things interact with each other. All right, so just like the human blood system, that it has a buffering system that keeps our pH in the range that keeps us from getting very sick. That buffering system is the same. It's the carbonate buffering system. And a buffering system is basically a natural way in which nature can resist change. Okay, so rather than the pH moving all over the place, we get this chemical reaction that will help the system resist that change. So if we have water with a lot of carbonates in it, specifically calcium carbonate and sodium bicarbonate, that's the type of system that will be highly buffered. I don't think that was me. Highly buffered and resist large changes in the pH. So that will keep the pH a little bit higher. Okay? Over here, though, with our malted barley, any malted barley has a little bit of what we call phytins. It's a phosphate structure that can react with calcium and ultimately generates some hydrogen ions that drives down the pH. It adds to the acidity. Okay? And the more we roast it, the more of that substance that's found in the barley. Okay? So if we want to get a balance here, the idea is the more alkaline the water, the darker the malts you want, or if you have dark malts, you better have highly buffered water, otherwise your pH will be too low. Or if you have high alkaline water with a lot of buffering capacity and you try to make a Pilsner with really light malts, your pH is going to be way too high. Okay? Or to summarize that on this slide, okay? The Pilsner that hopefully you all are enjoying now, ideally is produced with water with very low alkalinity. And over here, our stout is best produced with water with very high alkalinity because those dark malts will drive down the pH. The alkalinity balances that, okay? Lo and behold, people were doing this long before we had this understanding of the chemistry, right? Where does this beer come from? Czechia, Czech Republic. Sorry, my laser didn't work. I was trying to point there. You're right, this one's Ireland, Czech Republic. Very soft and low alkaline water. Hard, high alkaline water over here, right? Brewers have known this for a long time. It was from empirical evidence, but now we understand, and that's also what made this beer the envy of the world. And as soon as we mastered the water chemistry and understood how to manipulate water to get it the way we want it to, that's when it spread all over the place, okay? I really don't think that's me. Okay, so to wrap up the mashing part so we can have our next beer, the outcome of the mashing is what we refer to as wort, and wort is simply sugar water, okay? We've gotten all those starches, we've converted them into sugars, and we're pulling out the wort along with the proteins and nutrients and other flavor agents that we're going to move all the way through the process, okay? So with that, I'll introduce our next beer. And we're going to go to the other end of the flavor spectrum here. Quick quiz. What kind of water do we want for this? High alkalinity or low alkalinity? Oh, you guys are listening. Good. All right. So tonight we have another really great classic style, a great representation of this classic style. It's the Milk Stout that's put out by Tractor. And this one is brewed with, as you can tell, some great dark grains, both roasted and chocolate malts. That's not like the chocolate malt you had when you were a little kid. These are malts that are roasted in a way that actually makes them taste like chocolate and coffee, even though it is entirely barley. And another fun twist on this style of beer is that lactose is added to it. Any guesses to why we would add lactose to a beer? Make it milky? It makes it sweeter, right? But we already made a bunch of sugar. We had plenty of sugar in there. The key with lactose is that it can't be fermented by yeast. So you can add some sweetness and the yeast won't ferment it out. It stays in there as a residual. Okay. So I'm going to keep on rolling with the boil. Okay, so we're going into the next step of the process. So now we have our wort, and we're going to move it over into the boil kettle. And there are a lot of reasons why beer is boiled. Here are some of the highlights, though. The one I'm going to emphasize is the top one. This is when we add hops to the process. But we also want to accomplish a few other things. One is we want to concentrate the wort. So we boil off the water, and the sugars stay behind. We want to sterilize the wort. I think many of you have probably heard the legends of why beer was drank throughout the Middle Ages, and that's because it was safer than the water. Right? They could have just boiled the water. I don't know why that didn't occur to anyone, but probably no one wanted to say anything. And it also has some impact on the color and flavor of the beer. So let's jump into the boil, but I'm going to emphasize the hops aspect. Hops, Humulus lupulus, is an amazing plant. This is some of the more popular hops that are used in a lot of the beers that you probably have enjoyed. And this is known as a flavor wheel. You can get an idea of what the characteristics are of these different hop varieties depending on where they land on here. So if you know of some of the hops that you read off the board over at Bosque or something, then you might see some of these that you like up here. But we add hops for a variety of reasons. Some are probably obvious to you. It bitters the beer, and you need to have some bittering to offset the sugars that are in there from the malts. It also contributes to the flavor and aroma of the beer in ways that you're probably familiar with. And it's also a really important preservative. And that was one of the main reasons why it was used so broadly in times before we had good sanitation, was because of the preservative qualities of the hops. So, an interesting thing about hops, I want to emphasize the difference between bitterness and hoppiness, because a lot of people use these two back and forth, and they're completely different concepts. Okay, they're both concepts that are derived from hops. The hoppy part being pretty obvious. They both come from hops, but it's how you use the hops that drive one of them over the other, or you can have both. What it comes down to is the boiling of the hops. So let's say we boil the beer or the wort for 90 minutes. What happens is the longer you boil it, the more bitterness that comes from those hops. Okay? So after about 60 minutes or a little bit more, you've kind of maxed it out, but you're generating bitterness. Okay? And what's happening is our friend, the alpha acid, is going through a process referred to as isomerization, which hopefully some of you saw back in chemistry class at one point, right? But we have the same chemical formula, same basic structure, but we flip one of the rings here, so the groups switch. And with that little switch, we move from an acid that has no bitterness to high bitterness and no preservative qualities to high preservative qualities, okay? So that's happening. And that is driving what we call the IBUs, right? So if you walk into a brewery and you see the beer has 52 IBUs, what they should say is, we isomerized our alpha acids to this degree, right? I don't know why that hasn't caught on yet. But it's not, again, the only thing that hops are bringing to the party, right? If we add hops later in the game, closer to the end of the boil, we get different characteristics out of them. If we add them in the last 15 to 30 minutes, that is what contributes to the flavor, because only a small amount of the hops are able actually go through the isomerization process. And actually what's adding the flavor and eventually here the aroma is oils in the hops. And oils are volatile, so if you boil them for too long, you lose it, okay? So you add these things late, and then we come in at the very end and we do another one. And those are where we get the aroma, because you can imagine that that stuff is extremely volatile, the aroma agents. So you add that really towards the end. And in fact, a popular trend now is to even add hops after the boil is over and even in the fermenter. And we refer to that as dry hopping. I don't know why it's not dry, but it doesn't go in the boil. And so like a popular style now is the New England IPAs, the juicy IPAs that I'm starting to salivate right now, because those are so nice, right? Those have almost no bittering hops. The IBUs are very low. They add a bunch of hops very late in the process and in the fermenter. And that's what gives you that really juicy, wonderful aroma and flavor, but without the bitterness that some people really don't like. I do. All right. Just a quick preview of how we break these things down. So we got the different acids. I was afraid this wouldn't be readable, but all these bars are different hops. So the brewer can go take a look at it and see, okay, how much alpha acid do I have? How much of the different types of acids do I have? How much of the different oils do I have? And knowing that different oils contribute different characteristics, they can design a beer and think about, I'm going to add this hop early, this one middle, and this one late, and that's how I'm going to design this beer that's going to give me the qualities that I'm looking for. Okay? All right. Yeah, this is just blowing that thing up. And there's way more. If there's a bottom line to it, there's only 4 ingredients and 400 varieties of each of them. All right. Okay, so to wrap up the boiling component, we still have wort at the end of it. It's the same product as what came out of the mash, but now we've got the hop products in it, basically. Right? We've got the alpha acids, some of them isomerized, some of them not, depending on how we executed it. And we've got hop oils that are adding all that aroma and all of that flavor. So with that, I'll introduce our next celebrity, which is the Pub Ale from Sidetrack. Sidetrack flies a little under the radar just because they're a little bit of they are a small brewery, but I really recommend checking them out. They're on 2nd Street in Cole, downtown. Cute little tap room, nice patio, and they've got a pub ale. And this is a beautiful beer, okay? So it's moderate IBU, but it's on the bitter side because it's all added early. And specifically in this beer, they use East Kent Golding hops. And this is when you're really becoming a beer geek, when you're thinking, oh, I don't know about the East Kent. You know what they say about those guys. But you can start to get this flavor. Well, I like Columbus hops, or I like these hops. You can really start to develop that characteristic. And these are just really classic hops from Britain that give you a really classic pub-style ale. This beer also has a little bit of diacetyl in it, which is like a little bit of a butter or popcorn. And that's actually, in many beers, considered an off flavor, something you don't want. It comes from the yeast. And this beer is considered desirable. It's true to the flavor, or true to the style. And if you go to Britain and you have this style of a beer, this is what it tastes like. So please enjoy. Why don't I get any of these?
Because you didn't ask for it.
I'm done. And now I got 3 things to balance. What could go wrong? All right. So our last ingredient is the yeast. And this is perhaps the most unsung, yet really important to the final character of the beer. These are some giant blown up yeast with a scanning electron microscope. Those aren't socks. So there's a famous expression, unattributed expression in the brewing world that everyone's familiar with if they've made a few beers, and that is that brewers make wort and yeast make beer. And it's a really true adage, right? We can only do so much. We can set up the stage, but it's up to the yeast to take it home for us and really make beer at the end of the day. And what we're going to do is ferment, and ferment is changing sugars into two byproducts that we enjoy. Okay, alcohol and carbon dioxide. I think I'll go through these quickly, but this is the fermentation cycle. This is something that many chemists have spent their lives on, going into all the little nitty-gritty and details of this. Back to the engineer. I am an engineer, so I know as much chemistry as I need to pull off whatever it is I'm trying to accomplish. But what the yeast are really trying to do is up here at the top where they're just turning glucose into 2-pyruvates, and they're doing that because they're trying to generate energy. If you remember something from your biology class, from cell biology, right, that ATP is the currency of the cell, that's what they're trying to do. The rest is just to keep the system moving, okay? They're not trying to make alcohol for us. I mean, we can be grateful for it, but that's not actually their goal, right? That's a byproduct. So right away, they kick off some CO2 as the first waste product, which gives us nice carbonation in our beer, right? And then just in order to keep their electron chain going, they need to come back across and they generate these ethanols. So recycling, okay? It's environmental to drink beer. All right. And for the astute observer, I told you we don't really produce a lot of glucose, right? But fortunately, yeast cells have a special enzyme called maltase, which allows them to take that maltose and break it down into 2-glucose, and then they're off and running. Okay? So again, Mother Nature is just so generous to us. What's the Ben Franklin quote that beer is proof that there is a God and He loves us, or He wants us to be happy? I think that's what it is. Okay, a little more on yeast. Broadly, we can separate yeast into a couple of different categories. One is the first one being lagers. This is more or less like your German-style beers. The Pilsner that you guys had earlier was a lager. The key here is that it's fermented at a lower temperature. The yeast tend to be towards the bottom of the fermentation vessel, and you end up with a beer that is cleaner. It has less fruity characters. Unlike the ales tend to have a little bit more character to them. They ferment at a warmer temperature, and the yeast tend to accumulate towards the top. And then the oldest mechanism, which is was largely ignored and forgotten for quite some time due to industrialization of the beer brewing process, but now is getting a lot of love, is the wild yeast that produce some of the cool sour beers that are becoming pretty popular nowadays. And I'm going to expand on that in just a bit. Okay. This was a really neat project by White Labs out of San Diego, where they did a bunch of genomic sequencing of all the commercial yeast strains that are out there. So this is the family tree for the humble Saccharomyces cerevisiae. Okay, and you can see where they originated from. And what was fun about this particular study is the way that they ended up grouping these is they had these down here that they're calling beer 1. And I like beer 1. I like beer 2 as well. Beer 1 are the domesticated yeast, the laboratory cultured. We've been working on these forever. You can go over to the homebrew shop and pick one of these up. Beer 2 are the ones that we're rediscovering, the ones that exist in wild beers, that exist in Belgian lambics, etc., that we're just now starting to get a handle on. And they're quite different. It's on the other side of wine and whatnot. Okay, so a tremendous amount of variety within these yeast strains, and still a lot to learn. Okay, yeast, in addition to producing that CO2 and the ethanol, they produce a lot of byproducts, especially the ale yeast that I mentioned. And these byproducts can work with us or against us, depending on the circumstances. So a goal of the brewer is to create the conditions that are just right, that we get the things that we want and avoid the off flavors. Okay? Two of the groups that really contribute a lot to flavor, especially in ales, are esters and phenols. So For example, this, a lot of people call it 4VG because no one can remember that whole thing, but the 4-vinyl guaiacol, for example, gives Hefeweizen a clove-like characteristic. Okay, so that's an example of a phenol giving us additional character in our beer. Okay, so at the end of the fermentation scale here, what's coming out of it is beer. So that's our main product at this level, which allows us to introduce our next beer. So we are fortunate that Lecumbre donated a keg of their really nice, very classic and delicious Hefeweizen. And this is a beer that features that 4VG. Okay, so when you do get a chance to enjoy this, see if you pick up the clove, you're going to get a little bit of banana, right? No clove was injured in the making of this beer, okay? It is all coming from the yeast. It is a byproduct of the fermentation process, a very, very delicious byproduct, okay? Quick anecdote, so the particular yeast strain that Lecumbre uses in their Hefeweizen is sourced from Bavaria. It comes from the Andech monastery near Munich, and I highly recommend a visit. In fact, we led a class that wasn't all about beer, but we did have a class to Germany this past summer where we took 22 Lobo engineering students to Germany and Holland, and we wanted to make sure they got the full cultural experience. So beforehand, we toured Lecumbre Brewery, and Jeff Irway, the head brewer over there and owner, provided us with an orientation on German beers. He loves them a lot. I think he's still talking over there, actually. He really was excited. And we really appreciated that. And then he was generous enough to donate some yeast to us from the Andechs, where the students then joined us and we homebrewed it. And we split batch it, actually. We put in the Andech Hefeweizen yeast in half and just a clean American ale yeast in the other half, so the students could just completely see how that particular yeast strain, you would never guess that was related beers whatsoever. Completely different characteristic from the two, okay? And then we got to go check it out in person, so, just doing our research, okay? All right, so we can bring that beer out if it's ready. Almost, it's getting there. While the beer continues to pour, I'm going to switch gears a little bit and talk about some research that we're engaged in here at UNM, working on some traditional beers back in Belgium. So this is a study that we're just getting into press right now. And has anyone in here heard of lambics? Here or there. Right, it's an ancient style. You can go get some at Total Wine and then just dump it down the sink. It's terrible. You can't get the good stuff here, unfortunately. I shouldn't say that. It's hard to find here. You can go to Rowley's in Santa Fe, and they carry it. Just make sure you save up before you head up there, okay? Because the truly traditional made lambic is phenomenal, but it is hard to find in the U.S. because it's a quite limited product. So our goal here is we've been investigating how climate change, oh, thank you. I'll be right back. Ooh, clovey. Hefeweizen also, as the name implies, Weizen is wheat, right? So it's a beer that has, roughly 50% of its malt bill is actually made of wheat in addition to the barley. Okay. So with this study, again, we're looking at impacts of climate change on this traditional beer style, especially as it's influencing actual traditional breweries that are still making it the old-fashioned way and the really delicious way. We're specifically collaborating with a very respected and renowned brewery referred to as Cantillon. If you ever have the chance to visit that part of the world, I highly recommend dropping in there. They're also a living museum, so you can really learn about this process and its history and its culture. But this is a beer style that's been around for hundreds and hundreds of years. And this particular brewery was founded in 1900 just because that's when they bought it from the prior owners. The building itself has been there much longer. They're now fifth generation family business and, like I said, a functioning museum. So the question is, what makes this beer so special, if you ever have the chance to enjoy it? And really what's unique and magnificent about it is that they don't add yeast. Okay, I know. What? So this goes back to, so as another quick aside, the 4 ingredients. There's this principle, or there's a law called the German Beer Purity Law, the Reinheitsgebot, and they list these 4 ingredients. Yeast was added somewhat recently, after Louis Pasteur figured out what it was. Okay, before that, the gods made the beer, right? And things happen. This is the way beer used to always be made. Right? You would maybe recycle your yeast from the last batch, but you didn't have a laboratory culturing your yeast. And what these guys do is they brew their beer all day, and then this is a shot from their attic. This is a giant copper tank, referred to as a cool ship. At the end of the day, they pump their beer up into that tank, and they let it cool down all night. Open rafters, as you can see back here, wood beams, and what comes in, comes in. Okay? Are they crazy? I know, they're doing something right, okay? And the catch here is that the conditions have to be right. Okay, the conditions have to be right. And what it comes down to, oh yeah, and then the other thing they do is they age it for 1 to 3 years, depending on the style and what they're trying to accomplish, okay? But what I mean by the conditions need to be right is during their brewing season, which is during the winter, they need overnight low temperatures between 8 degrees C and -8 degrees C. So that's, I don't know, I'm terrible at these unit conversions, but like 20 to 45, something, 46, okay. So around the freezing range. If it's much colder than that, there will be nothing in the air and the beer won't ferment, nothing will happen, right? If it's too warm, there's everything in the air and they will make vinegar and other awful things that no one's going to buy. Okay, so they need just the right temperature range for this to be successful. So this is a concern, all right? So this is one of the issues that we've been investigating with them is, well, how have these conditions shifted over time? And then the other side of this is that they're aging it in these barrels for years. They want it to get warm in the summer. The expression is that lambic must go through at least a summer before you can drink it. It adds character to the beer. But if it gets too warm, like the heat spells that they've been experiencing recently, it can spoil. And they've had to dump, this year also was quite a challenge for them, but they've had to dump as much as 6,000 liters, and this is a small family business. Right? That is a lot going down the drain because it got too warm. Okay? So we've been working with them to understand how climate change has influenced and potentially will influence in the future their production methods. So one of the things we looked at, for example, is how these overnight low temperatures have changed over the last, well, back to 1900 when they started brewing at this location. We compared these statistics and these numbers to their brewing records that also go back way well into the last century. And then we also looked at climate change projections going forward to get an idea of what they might expect in Brussels and over the rest of this century. And one of the stark conclusions that we've seen is that the number of days where they can actually potentially brew has dropped by about 45 days over the last century. And if you follow the trends going forward, regardless of which climate change projection you look at, they're looking at under 100 days per year that they're going to be able to brew. And we've gotten to understand their process even better, their history even better, that they used to brew in the fall and the spring and have to stop for a while in the winter because it would get too cold. Now that's not a problem. Instead, the season's just shrinking on either side. And they used to brew from October until early May, and now it's November into maybe March. Okay? And then on the warm side, summer highs are through the roof. This past summer broke records again in Europe. They actually had this up and down that was crazy. They had the warmest May on record, one of the coldest Junes, and then they still set the record high for the summer because July and August were so warm there. Okay. So we've also been working with them on continuously monitoring their system. So we've added temperature sensors and a weather station, and we're trying to help them get a better understanding on how their process is working and how it's being influenced by temperature. This is just an example of some of that. We'll skip through that. And then we've also been talking with them about adaptive strategies because they are very true to the culture behind their beer and their process. This is one of the very few, like out of 3 or 4 breweries that survived Budweiser and Heineken and all the macro movement. So they survived this really severe economic shock. So they are very proud of their process. They don't want to shift away from what they've been doing, but there are some things that they can possibly do. So we've been talking with them about how they might incorporate some of those things into their process, and some are more desirable than others. Because, for example, artificial cooling, first of all, they really don't want to do that because they feel like it will reduce the quality of their beer. And then there's also just the sad irony of fighting climate change by refrigerating things, and refrigerants are one of the biggest CO2 footprints out there. So they really don't want to do that if they don't have to. And then same thing on the cellaring side. Okay. So in summary, with that work, we're seeing that they have experienced already pretty drastic change, and unfortunately the projections show that it could really be a problem for them, and it's going to be tough for this small family business to adjust. And we've also tied that to the cultural heritage of the region. Okay, just quickly, this was kind of fun. This work took off last week. We were in The Guardian and a couple of other it went into syndication, and we had friends texting us. This showed up on my iPhone where the research was really getting out there. So it was kind of fun and kind of also sobering, I guess is the right word. But we work on all these scientific issues. We're looking at climate change in the Himalayas and in Patagonia. I swear that's not me. And and no one shows much interest. But as soon as you put something out on beer, like everyone's calling and yeah, what beer? But what about the children? Yeah. Stop whining. Yeah. So Jeff had asked me about my favorite brewing experience, and this one is what came to mind. So this is Jean Benoit. He's the head brewer and main manager at Cantillon, and we had the great fortune of being at Cantillon on his 50th birthday last year. So that was the 50th birthday reference, and we made a very special beer. He modified the recipe to make it more closely emulate a very traditional recipe. It had a much higher wheat proportion than in the past, and a very different hopping schedule. So it's going to be really fun to try that in 3 years or so. Maybe for my 50th it'll be ready. All right, so with that, let's say cheers. I don't know if John maybe has anything else to say.
I would say if anyone has any questions.
Yeah, we could definitely open up to questions. And also, I missed if it was announced earlier that the tap room at the other end of the sub will be open to people with your red wristbands. So if you want to continue some discussions over a pint down there, we can do that as well. And this is their kind of grand soft opening, so we're really lucky to be able to sneak in there. So yeah, happy to take any questions. Yeah.
Can you talk a little more about those wild yeast and sours and stuff? It's not something, I've tried a few of them, but what makes that? Can you talk a little about it?
Yeah, so the question was, what makes sour beer sour, basically? What are these sours all about? And so what's really giving you that puckering sensation is acidity. Okay, and acidity is being generated by bacteria. So there are 3 or 4 primary bacteria that kick in at different phases and generate that kind of a puckering sensation. With these traditional methods, those different bacteria kick in over very long periods of time. So, and there's some really neat charts that show, people have done the flow cytometry and genetics on it to see what's kicking in and leaving at different times. And it takes at least 18 months to make a good traditional sour beer. Nowadays, there are still some good versions on the US market, but most of those sour beers that you get on the US market use a technique called kettle souring, where the brewer specifically adds lactobacillus, which produces lactic acid, and you can do that very quickly. So you can still make a sour beer, but you can make it in an economic and rather short-term period. You can still make a very nice beer that way, but it's not near as sophisticated and complex as these ones that take years for the different microbes to kick in, and then the next one uses the byproducts from the last one, and all these different products. But basically, it's acidity and other neat off flavors that come from both the wild yeast and bacteria working together in this microbiome. Cool. Thanks. Nice question. Yeah.
As a research administrator, who helps fund your nice work with your
Yeah, so that work was funded.
sorry.
Yeah. Yeah, so the Belgium work was a passion project that came out of my wallet. Okay. Yeah. Yeah. You're all welcome. Yeah. I'm no hero. I'm just a man. Okay. But yeah, we do hope to get some funding for that at some point as we get a little track record here. But if you want to write to NSF and say you want get money to go to Cantillon and drink beer, it's a tough sell. You want some preliminary data and a couple publications out. So that one's self-funded so far. Yeah, sure.
Can you talk a little bit more about the...
Oh, sorry. We'll come back to you.
Barnyard quality?
Barnyard, yeah.
What was that?
Yeah, it's not one of my favorite descriptors. For one thing, it doesn't sound all that attractive to begin with. And second, I grew up on a farm. And whenever people drink one of these beers and say, oh, I'm getting a barnyard, my first thought is, you've never been in a barn, have you, buddy? But one of the most well-known wild yeast strains is known as Brettanomyces. And that particular yeast strain produces this character that we just don't have a word for. It materializes in different ways, but it's got this just cool funkiness that people call, even worse, horse blanket. Yeah, it's just the worst descriptors, but the flavor is incredible. So until language catches up with us, but that's what I was referring to, and if I can share one with you sometime, maybe I can help illustrate the point. I think you really have to taste it to get it. I don't like barnyard. I almost didn't put that up there, but there's no other one to call.
Flavor from cider.
Yeah.
Like that.
Yeah, yeah. Yeah, it is kind of a cidery character, absolutely. And this particular beer style, Lambic, for our friend Jean describes it as being at the intersection of beer, champagne, and cider. But it really sits kind of in that neat realm. Back to the sourness as well. Right? Yeah, I think there's one up here. Yeah.
Yeah, I had a question. Could you talk a little bit more about what constitutes an IBU and what the general range of IBUs is for beer?
Yeah, so the question is about a little more background on the IBU concept. So so first of all, there's two ways to look at IBU. One is theoretical and one is measured. And when you see IBUs up on the chalkboard at the brewery, it's always theoretical. And what they are doing is looking at the alpha acid content of the hop itself, how much you add, so how many grams or how many pounds of that hop have been added, and then how long did you boil it for? Assuming that if you boil it for more than 60 minutes, all of the alpha acids have been isomerized and converted. So the range can be 0 if you had no hops. On the high end, in reality, you can't really get above about 100. Okay? Sometimes you'll see 120 and 130, something like that on the boards. That's just because they're doing the calculations and it came out to be 120 or 130 because that's past saturation conditions for the isomerized iso alphas. So 100 is really about what you can do, and that is quite a puckering beer. I mean, that is like Lecumbres, Elevated is in that range, and it is a puckering beer. It's lie down and have a nap once you finish that one. But it's delicious, totally delicious. Yeah. Anything else? Yeah.
Remember, when it's exposed to the air,
Mm-hmm.
what are we picking up here? It's absorbing something, correct?
Yeah, so it's wild yeast and bacteria. From is a good question. So, a lot, kind of like the wine world has this concept of terroir, that it's from that place. That's also what makes lambic beers very special. Is that the microflora in that region is very specific, both to the region in general, so just what happens to be floating by, But also, if you look at a place like Cantillon, where they've been brewing that same beer in that same building for a couple hundred years, as soon as you step foot in that building, you smell and take in that microflora. It becomes part of you. All your clothes smells like it, and it's wonderful, and you don't want to wash them, and you just want, sorry, I'm getting personal. But, but it is really specific to that condition. And then the other thing that happens is it's in the rafters, it's in the wood, it's everywhere, and all day long they're brewing, and the whole building fills up with steam. And that steam starts to liberate things. You can tell, you walk in the morning and it's cold and you don't get nearly the aroma. By the end of the day, all that steam has risen up through the building, gotten through the rafters, and it releases a lot of that microbiome. So a lot of it's coming from the building itself. And then to some degree, they're also picking up the microflora from the barrels. So they reuse the barrels over and over. They do clean them out really well and sanitize them, but there's still some microbiome that persists within that wood that is also carried forward. So it's just represents that area. People can make these type of beers, and people do make these beers in other parts of the world. They taste different. Like, it doesn't taste like the Belgian Lambic. There's some really nice examples. But they're different because you have different microflora.
All right.
Everyone ready for a pint? Oh, I have my beer.
Well, hold on, I just, how awesome was that? No, you just stay there. I mean, that's just absolutely incredible. And thank you so much.
Thank you.
And thank you, Dr. Rack. So first, just a little expression of our gratitude here.
What? I've got, oh,
Oh, no.
thank you. Appreciate it.
So just a little bit of a reminder, this is homecoming week. And for all of you alumni, we'd like to see you at the tailgate party, 1 o'clock, starting at Dreamstyle Stadium on Saturday, and follow that up with the game. Also, this is especially awesome out of a completely awesome group of Lobo Living Rooms, and thank you very much to both of you again for that. Not that there's an underlying theme here or anything else, but the next one is on November 1st, and it's called Rare Treasures and Fine Wine, and it will be at Zimmerman Library. There may be a snort or two there as well. So anyway, well, thanks so much for our speakers. Thank you very much. It was a great experience. And go Lobos. See you at the tailgate party, and see you down there at the tap room.